Good morning, everyone. So let us continue with our discussion on group 14 elements. So in the previous class, we introduced ourselves to the various elements that are in the group 14 element, that is your carbon family. And we looked into the allotropy as well as the electronic configuration and the oxidation states that these elements show. So as we discussed in the previous groups, we always looked into the first element of the group, and we found that first element always shows some anomalous character. And from the previous discussions, we know that these anomalous properties that these first elements show is because of their small sizes, or it's because of their high ionization energy, or it's because of their high electronegativity. Okay, all these reasons combined together give them this anomalous property that these elements show. Now, because of these small size, high ionization energy, and high electronegativity value, most of the compounds that these elements form are non-metal. So carbon in this case is a non-metal, and therefore it doesn't form any cationic or positively charged species. Okay, and and all these reasons combined give it the covalency or the tendency to form the covalent compound. Now let's individually look into some of the peculiar behaviors or the anomalous property that the carbon have in comparison to the rest of the elements in that same group. First and foremost thing that you here would like to know is that they only form 4 bonds. These carbon are able to form only 4 bonds. Now this is very easy to understand because this thing we have already done when we discussed about the boron as well. That is mainly happening because these elements have in their electronic configuration. So these elements in their electronic configuration, as we saw in the previous class, it is nothing but 2s2 and 2p1. Okay, so if you write it in the box form, okay, it would be something like this in the ground state. Okay, you will have the 2 electrons occupied in the, so this would be the ground state electronic configuration. Now when we talk about, sorry, it is 2p2, not 2p1. So it should be more electron here. Now, when you talk about the excited state, it should be written as so the excited state, these paired electrons are kind of excited, and the electronic configuration in the excited state is something like this. So apart from these, so this is your 2s orbital and these are 2p orbitals. Now apart from these, you do not have any other orbital present in the second subshell. That is, only s and p orbitals are present. So total of 1, 2, 3 and 4 orbitals are only possible, which is available for any kind of bonding. And that is why carbon only forms the 4 bonds in this particular case. So this particular thing only is possible in the case of carbon, because the other elements in the group, they have like when we come to silicon, the electronic configuration is 3s2 3p2, and at that time I told that it also has a 3d subshell which is empty. So it also now can participate in some form of bonding. So it can expand, the silicons can expand its valency beyond 4. Okay. However, the carbon can only form 4 bonds, and that is why that is one of the important property that these particular groups show. Now you will find certain compounds in which the carbon shows a coordination number that is more than 4, but those are very electron deficient compounds. and they are basically multi-center compounds. Like when we did the diborane, the hydrogen, which is able to only form one bond, is able to now form two bonds in the bridged bond, right? But these are electron deficient bonds. That means two electron, three center, two electron bonds. They are electron deficient bonds. Okay. Similarly, carbon compounds, carbon also can form higher coordination number, but those are not the usual two center two electron bonds, but they are multi-center electron bonds, and they are electron deficient in nature. So in that, you might see a higher coordination number than four, but those are not the usual thing that we are talking about here about the covalent compounds. So here, when we talk just about the two center two electron bonds and we talk about the normal covalent compounds, there carbon can exhibit only four bonds. They can only form four bonds. Now, another property that is very peculiar to the carbon element is that its ability to form multiple bonds. Okay, this is very, very important property that the carbon shows. And because of this, you will have the multiple bonds, like you will have the alkene. Okay, you also have alkyne formation. Okay, and you will have carbonyl compounds. Okay, and you have also imine compounds where you have doubly bonded nitrogen. You have also carbon sulfides having a doubly bonded, and these multiple bonds, these carbon can form very easily because of this p pi p pi pi overlap, p pi p pi pi overlap, and that is very unique to the carbon, because the 2p orbital are in right energy level, as well as their shape and their availability is so perfect that it is able to form such kind of p pi p pi bonding with the other elements like itself, or nitrogen, oxygen, or sulfur. With their p orbital, it can form perfect p pi p pi multiple bonds. Now, this p pi p pi bonding is not possible in the case of the other elements, like in the silicon. Silicon, the p subshell is basically 3p. And 3p, if you compare with 2p, they are larger in size. So if you compare size-wise 2p and 3p, 3p is larger in size than 2p. And when these orbitals are becoming larger in size, they are more kind of expanded and they are more diffused. Okay, and because of this diffused nature, they doesn't form a very perfect p pi p pi overlap with the elements such as carbon or sulfur, oxygen, or nitrogen. And that is why these elements, like after this 3p, 4p, 5p, all these elements doesn't show a very effective overlap. They doesn't show any effective overlap. And that is because of the large and the diffused nature of the p orbitals present on them. And that is why this particular effective p pi p pi multiple bonds is only possible in the carbon because 2p orbitals are in the right energy level to form such multiple bonds. And that is true only in the case of carbon. We find this peculiar property because 2p orbitals are also available in the case of boron, but they don't form much of these p pi p pi overlapping or multiple bonds, but they are in the right configuration, in the right electronegativity, and the right uh, perfect orientation or something, that they are so much perfect in condition that they form very effective p pi p pi overlap. Another very important property that these elements show, and that is their ability, and that is called catenation. Catenation means they are, this is a property by which carbon can form long chains. Okay, so you have come across alkanes. So you have not just methane, you have ethane, propane, butane, pentane, hexane, heptane, nonane, decane, dodecane, a lot of them. are there. So it's because of the formation of long chains. Okay, and that long chain is possible because the carbon-carbon bonding, that is the CC bonding, is very, very strong. So if I talk about the bond energy, it is almost like 348 kilojoule per mole is the bond energy of the CC bond. And because of this high strength of the CC bonding, they can kind of sustain longer chain. However, as you go down the group, these bond energies decreases. Like in silicon, it is 297. In germanium, it is 260. And in tin, it is 240. So you see how much drastically it is reducing. So that is why carbon only shows higher catenations, or they form really large long chains. However, silicon also forms long chains, but they are not to that extent as you find in the case of carbon. So this is a very, very important property that these carbon compounds show. Okay, and that is because of the strong bond energy of the CC bond. Now here I have put two different molecules. One is your trimethyl ammonia, and another is tricylyl ammonia. Okay. Now, what I would like you to do is, while will be discussing about this in the live session, try to find out what would be the shape of these two molecules. Okay, and use any approach, whichever you are convenient with, either VSEPR approach or the BBT approach. Please use them. I'll be asking one of you to solve that this particular structure, and let me have a good answer from you. So for now, thank you very much for your kind attention. Let's have the discussion in the live session. Thank you very much.